Good morning. Good morning. Hope everyone's doing well. I really stupidly stayed up too late last night, and now I'm pretty tired this morning. Am I up to 15 people yet? I'm only at 12 people. Now I'm at 14 people. All right, I'm going to go ahead and continue my review. So let's see. Oh my God. Going to continue my review. A couple things about the final. So the final is available. It ended up being 18 questions. You get 2 attempts. It's due next Friday at midnight, so you can take it twice between now and next Friday at 11:59 p.m. And there will be a curve. I'm not sure how large the curve will be, but there will be a curve. And yeah, so that's the final. So I'm just going to keep reviewing and trying to get through as much as possible. I'll probably go for about 30 minutes or something, because really I want to give you guys time to study, to get caught up on assignments and that sort of thing. All right. So I believe that in the video that I posted for Tuesday, I was able to cover material through energy. So I'm going to start out today with momentum. All right. And so momentum is denoted by P, and it's equal to m times v, mass times velocity. Momentum is a vector in the sense that you can have positive momentum or negative momentum. The total amount of momentum is just going to be P1 plus P2 plus P3 plus however many things you have. And the important thing about momentum is that it is conserved in a collision. So the total momentum before the collision is going to be equal to the total momentum after the collision. Okay? And so that's pretty useful. We talked about completely inelastic collisions. And in a completely inelastic collision, the objects stick together. So basically they become one object. So your conservation of momentum equation, you have m1 v1 that's the momentum of the first object, plus m2 v2, that's the momentum of the second object initially, equals, and then they collide and stick together, so now they're like one object of size m1 plus m2, and you can solve for whatever you need to solve for in this equation. So yeah, in this type of a collision, kinetic energy is turned into heat. All right, so you could calculate, if you wanted to calculate the kinetic energy before, you would do 1/2 m1 v1 squared plus 1/2 m2 v2 squared, and then the kinetic energy afterwards would be 1/2 m1 plus m2, because remember they're collected together as a single object, times v final squared, and you take the difference of those, and that's going to give you the amount of heat that is released. Okay. We also talked about impulse. Impulse J, which is equal to, depending on the information that's given to you, it could be equal to force times time, or it could be equal to the area under the curve of a force-time graph. So it just kind of depends on what information is given. And the impulse is important because the impulse due to the net force is equal to the change in momentum. Okay, so that was momentum. Now, after momentum, I think we talked about circular motion. Okay. So when you're talking about circular motion, you have this object moving in a circle. The velocity of the object is tangent to the circle, and the acceleration points in towards the center. That's why it's called a centripetal acceleration. Centripetal acceleration means that center seeking, towards the center. So it doesn't matter where in the circle it is. If the object gets to a different part of the circle, then the whole thing rotates. Okay. We talked about the period, which is basically the time to complete a rotation. All right. And so if we know the period, we could compute the speed. The speed is going to be 2 pi r divided by the period. Okay. And then there's a formula for the centripetal acceleration, which it kind of involves calculus to derive it, so I won't derive it unless you take my class next year. But it's v squared over r, and that can also be written, if I plug in this equation for v, I could write that as 4 pi squared times the radius over the period squared. So Newton's second law applies equally well to circular motion as it does to linear motion. So Newton's second law, F equals ma, net force equals ma, we could also write it as net force equals ebb v squared over r. Excuse me. And in this case, the force, this would be the force that is making you move in a circle, and that force also points towards the center of the circle, and so it's called the centripetal force. one of the things that we talked about that was a little bit tricky was the idea of a vertical circle. So you can have a horizontal circle, which is a circle like this, or you can have a vertical circle, which is a circle like this. And so vertical circles are tricky because gravity is involved. Gravity is the centripetal force. So, when you're up at the top, you have gravity going downward, and your acceleration is going downward, because downward would be towards the center of the circle. If you're at the bottom, you have gravity going downward, but the acceleration is going upward, because now the center of the circle is above you. So maybe you have something like a road. Okay, so you're moving in a circle. There's a road underneath you that exerts an upward reaction force / normal force. So at the top of the circle, Newton's second law is going to be up force minus down force. So normal minus mg equals negative mv squared over r. So the negative is because the acceleration is downward. Whereas at the bottom of the vertical circle, we have normal force minus mg equals positive mv squared over r, because now the acceleration is upward. Okay. There are all kinds of different situations with different centripetal forces. You could have gravity be a centripetal force. You could have elastic force be a centripetal force. You could have normal force, friction. All of those things can be centripetal forces. And indeed, in this case, we have two centripetal forces. Okay? So that is circular motion. We talked about gravity, or gravitational field, which is denoted by G. And the gravitational field, by little g, I should say. The gravitational field is basically the acceleration due to gravity. All right. It's the acceleration due to gravity. And the value of the gravitational field is big G, big M over r squared, where m is the mass of the thing making the field. Okay. And r is your distance from the center of the thing. So you have to be aware of, there are problems where we talked about altitude. Okay, so r might be, if we're talking about a planet, for example, r would be the radius of the planet plus the altitude, because the altitude is the distance above the surface. Okay. Big G is a constant of nature. Its value is 6.7 times 10 to the negative 11 Newton meter squared per kilogram squared. All right. Once you know the gravitational field, you could calculate the gravitational force, which is also known as the weight force. And so the gravitational force is m times g, where this m is not the same thing as that m, okay? This m is the mass of the thing making the gravitational field. This m is the mass of the thing feeling the gravitational field. Okay? And this is the field that it experiences. All right? So it's the same equation as the equation for weight force, because gravitational force and weight force, they're synonymous terms. Okay? So then what we did is we combined circular motion with gravitational field to talk about orbits of planets. All right. And so if you are in an orbit, then basically the gravitational field is going to be equal to your centripetal acceleration, because gravity is the thing that is causing the orbit to happen. Gravitational field is G times big M over R squared. Centripetal acceleration, I'm going to end up using the 4 pi squared R over period squared. And so you take this and you cross multiply and you get Kepler's law, which is Gm period squared equals 4 pi squared R cubed. So this is a really useful equation. It says, so there are 3 variables in this equation. It's mass, period, and radius of the orbit. And if you know 2 of them, you can get the third, okay? So, if you know the mass, and by the way, this is the mass of the central body. That's the mass of the thing that is causing the orbit to happen. Lost my train of thought here. So if we were talking about, a satellite orbiting the Earth, then that mass would be the mass of the Earth. If we were talking about a satellite orbiting the Sun, that mass would be the mass of the Sun. If we were talking about a satellite orbiting the Moon, then this mass would be the mass of the Moon. So if we knew the mass of the central body and the radius, we could predict the period of the orbit. Okay? If we wanted to put a satellite into an orbit with a given period, this equation would allow us to calculate what is the radius of that orbit, or what does the altitude have to be, and so on. In my opinion, the coolest application of this is to figure out the mass of the central body. If you observe something in orbit and you know that it has a certain orbital period because you're looking at it orbit, you know it has a certain orbital radius because you are looking at the distance between the two, you can calculate the mass of the central body. So that's pretty cool. All right. Give me 1 second. I'm just going to double check what we covered next. Let me look at the I'm looking at my calendar for this class to see what I talked about after gravitational fields. Okay. I talked about uncertainties. Okay, so uncertainties. So if we have a value, and this is usually how it works in an experiment, you make a measurement that measurement is not 100% certain, okay? So you have, let's say you're measuring a quantity called x, okay? And so x maybe is equal to 5 plus or minus 0.2. I should technically say 5.0 plus or minus 0.2. So this number right here is our best guess. All right. And this right here is called the absolute uncertainty. Okay. So what that means is that x lies in the range from 5.2 to 4.8. All right. So there's a thing called the fractional uncertainty. Which is, and by the way, sometimes I will write this as x bar for the best guess and delta x for the absolute uncertainty. So the fractional uncertainty is defined as delta x over the best guess. All right. So in this case, it would be 0.2 over 5, which is 0.04. So basically, that's 4% is my fractional uncertainty. So it's a measure of how does the size of the uncertainty compare to the size of the value that's being measured. Okay. If you were making a measurement and it was 0.3 plus or minus 0.2, that's a horrible measurement because 0.2 is a huge portion of 0.3. So your measurement is basically all uncertainty. All right. So that's why the fractional uncertainty is a really useful concept. Now, oftentimes in physics, we are making a measurement, and that measurement isn't the final goal. The final goal is something else. Okay. So an example that just pops in my head is what if you wanted to know the specific heat capacity of something? So you have Q equals mc delta T, so you have rearranging that equation, you have this, all right? So what is your heat? That could be uncertain. You don't know exactly how much heat you're putting into the sample, all right? Maybe you're trying to determine the specific heat capacity by putting, a pot of water. What if you're trying to determine the specific heat capacity of water? You're putting that water over a burner, and you know how much heat the burner outputs. But it's going to be uncertain because not all of the heat actually goes into the water, right? It's like if you put your hand over the side of a burner, you can feel the heat doesn't just go into your food, right? The heat, some of the heat goes into the air. So, that's a little bit uncertain how much of that heat, even if your burner is outputting a known amount of heat, you don't know how much of that heat actually went into your food, okay, or the water or whatever. So this is uncertain. The mass of the sample, your scale isn't perfect. All right, your scale might say blit, point, blit, blit, blit. That's uncertain. Your change in temperature is uncertain. Your thermometer isn't perfect, okay? So all of these things are uncertain, which means that the value that you calculate for the specific heat capacity is also uncertain. And so this topic of seeing how does the uncertainty in a measurement result in an uncertainty of something that's calculated from those measurements, that's called propagation of uncertainty. All right. And so the way that propagation of uncertainty works is if you have two numbers that are added together, so if you have or subtracted, then that means, so if they're added or subtracted together, then the uncertainty, the absolute uncertainty in x plus or minus y is going to be the absolute uncertainty in x plus the absolute uncertainty in y. So notice you're never going to subtract uncertainties. So if two things are uncertain, that always makes the result even more uncertain. So your net result is never, you could never have two things that are uncertain and they somehow make it less uncertain. Okay, the combination of those two things being two things being uncertain will make it even more uncertain. Okay, so that's why it's adding, even though we could be subtracting the two things. Okay. So a good example of that might be a square, or a rectangle, excuse me. Okay, so maybe the width is w plus or minus delta w, and the height is, h plus or minus delta h. So the width and the height of this rectangle are uncertain. And we want to know, what is the uncertainty in the perimeter? So the perimeter is twice the width plus twice the height. So this is going to be two things added together. All right, and so when things are added together or subtracted, their absolute uncertainties add together. So it's going to be 2 times delta W plus 2 times delta H. All right, that's going to be the absolute uncertainty in the perimeter. If things are multiplied together, so if we had x times y, all right, then we don't, so anytime things are multiplied or divided, you don't add the absolute uncertainties, you add the fractional uncertainties. So the fractional uncertainty in x times y, that would be this, right? Because this is the absolute uncertainty, this is the best guess. So this is the fractional uncertainty, is going to be the fractional uncertainty in x plus the fractional uncertainty in y. Okay. So let's take this for example. What if I wanted to know what is the so I have C equals Q over M delta T. All right. And I want to know what is the uncertainty in specific heat capacity. All right. Because this is a bunch of things multiplied together, I would compute the fractional uncertainty. Okay. And that would be the fractional uncertainty in Q plus the fractional uncertainty in M, in mass, plus the fractional uncertainty in delta T. That's a little bit confusing. It's delta delta T. Okay. If I wanted the absolute uncertainty, I would then multiply this by both sides by C in order to cancel this out. So I multiply by C and that would get rid of that. Okay. So that's propagation of uncertainty. The next thing we talked about was calorimetry. I think I'm going to review, probably we'll just completely finish up the review on, or we'll come very close to finishing up the review on Monday. Because I don't want to, I'm tired of talking, I'm tired of reviewing, so I'm just going to stop there.